Hey everyone, today let's try to solve another LeetCode problem. Today's problem is called Modify Graph Edge Weights. This is a pretty difficult problem in my opinion. I probably wouldn't be able to solve it if it was asked in a real interview. So anyway, let's try to explain the problem description first. So basically, you are given a graph with n is the number of vertices and edges being the edge of that graph. And you're also given a source and a destination and a target. You need to return whether it is possible for the shortest path of this graph from source to destination to be target. One tricky part is that some of the edge, they can be -1, which means you can set any positive integer for the weight. And for the other edge weight, like this one, and you are not allowed to change them. So basically there are two types of edge. One is with -1 and one is with an initial positive weight. So with the -1, for example, in the first test case, every edge is a -1. So then we can just set from 0 to 3 as 3, and from 3 to 4 as 1, and from 4 to 1 as 1, and from 0 to 2 as 1. And by the way, I'm using this line to represent that this is a negative edge that we can assign some numbers to. So basically, if it is a dash in here, it means that the edge was -1. Now, if we set the weight in this way, and then we go from 0 to 1, we will essentially take this path. 3 plus 1 is 4. 4 plus 1 is 5. So this is the only and also the shortest path going from 0 to 1. So that's why this arrangement, this particular arrangement, is possible to reach this target. That's why we return this arrangement. Actually, this one doesn't matter, but you have to set it. It doesn't matter if it is included in your shortest path or not. You have to set some integer in it, which is a non-negative and non-zero integer, basically a positive integer. So let's take a look at the second example. Now, if we convert the edge into a graph, it will look something like this. From 0 to 2, the weight is 5, and from 0 to 1, there can be something that we have to set, and then we are going from source equals 0 to destination equals 2, and the target we want to reach is 6. So notice that no matter what we set here, 1, 2, 3, or 1000, doesn't matter, because this doesn't affect how 0 go to 2. That's why no matter what we set, we cannot reach the shortest path being 6, because it will always be 5. That's why we should return an empty array if such arrangement is not possible. So that's basically all of the problem description. Let's think about how can we actually solve it. Well, since it is about calculating shortest path, let's just consider Dijkstra's shortest path algorithm, because it makes the most sense. By the way, Dijkstra's shortest path algorithm is an algorithm finding the shortest path from source to destination. And we can do some modification on it to let it not only return the cost of the shortest path, but also the actual path itself. So that might be useful to us. But in general, the first thing that should come to your mind is that probably we should call Dijkstra, because the way to calculate the shortest path. And by the way, this might be also another reason why this is a hard problem, because if you don't know Dijkstra before, I think it's pretty hopeless for you to solve this problem in the interview setting. So what about just set everything to lowest first? Because we're gonna start from somewhere, and then why don't we just start from setting every edge to the lowest first and just run the Dijkstra and see what we will get. So we set every edge, every -1 edge specifically to 1. So that is the lowest edge path that we can reach for all the paths. So in the current situation, we cannot go even lower because we need to set the -1 to a positive number. So 1 happens to be the lowest positive number. So now let us just run Dijkstra and see what can we get. So let's say the Dijkstra return something like, okay, the shortest path is greater than the target. What does it mean? So if that is true, I mean the shortest path is greater than the target, then we just return an empty array. Why? Because we just set every -1 path to the lowest. We cannot go even lower. And that is already considered the fact that the shortest path includes some -1 path. So it is also possible that the shortest path does not contain any -1 path. But either way, if it is greater than the target, there's nothing we can do. We just return an empty array because we cannot make it even smaller. We already reached the smallest possible. But what if it is not? What if it is not, then we're going to check if the shortest path is the target. Well, if the shortest path is the target, then it means that, well, we just set every -1 path to 1. It means this arrangement is a good arrangement. So we just set every -1 path to 1, and then all the other path we just return as it is. Then we can form the answer in this way. But let's consider even more complicated situation. What if it is no? So the shortest path is not the target. Now we're gonna ask if the shortest path has x. Now, as I mentioned before, if there is a source, destination, there is a path like this, and all of them is like 3 to like this 2, 3, 4, or like 5, and there is another. So none of this is -1. It means that we cannot do anything for this shortest path. Now it doesn't matter how we change this -1 to anything else. It doesn't change the fact that this path will continue to be the shortest path that is smaller than the target. We cannot do anything to this shortest path that is smaller than the target because there's no -1 inside it. That's why if we meet something like a shortest path not having x, then we just return an empty array as well, because there's nothing we can do. But what if the shortest path is greater than the target and it's not the target, and it has some x that we can fix? Then what should we do? So what to do when the shortest path is smaller than the target, and we can increase them because there is some path that are -1. So imagine the shortest path is this. This path is the shortest path that our Dijkstra find. And this A and this Z happens to be a -1 path, which means we can increase something on it. And we can get the formula something like this. And by the way, B and C and D is some path that we cannot change the weight because they have some initial weight on it. So A plus B plus C plus D plus E, where A and E is the -1 path, is S, and S is strictly smaller than target. Then what should we do? Well, we can change A to E to plus equals to target minus S. Okay? If we set this, and then you will notice, by the way, I'm not changing both of them, A and E. I'm changing A or E. So E plus equals to target minus S. And after doing this operation, and then A plus B plus C plus D plus E will become target, because this is just how the formula works. And then we're going to set everything else the -1 path except A, obviously except every -1 path inside the shortest path if there exists more. Because we don't want to make them to infinity. Because if we make it infinity, it's not going to be having the same weight as the target. You might ask, why do we want to set the infinity? Is that because I really want this to be my shortest path? Because there could be another path like this to here. When I increase E, then obviously it will no longer be the shortest path, or it is possible that this path will not become the shortest path anymore because I increase E. There could be some other path here as reaching the destination from source, being the shortest path now. But I do not want that. So I'm going to make every -1 outside of this path to be infinity. So I'm just gonna, so I'm doing that because I really want this path to be the shortest now. Because if this path becomes shortest, then this will be the answer. So that's why I'm doing that. And I'm gonna run Dijkstra again and then see if now the shortest path is actually target. But is it really good enough? What if the next shortest path includes E or A? While we increase E, we try to make every -1 path outside to be infinity, but we didn't change this A. It could be a scenario that there is here, and this here, and this particular path become the next smallest. We could not change this A to -1 or to the infinity because we need to use this path to reach our target. So unfortunately, we cannot just stop by doing it once. We have to repeatedly change or do the steps that I have mentioned in order to make S equals target. So, and now you might ask, will that be an infinite loop? Because it seems like you keep doing the steps over and over again, but this will not be the case. Because every time we will set everything outside the path to be infinity. And I will also increase 1 E. So the next time I'm going to run the algorithm, the -1 path will at least decrease by 1 because I will no longer consider this. So in a worst case scenario, which is very rare, we have to do m times, which is the number of paths that we have, and it happens to be our -1. So that's pretty much the overview of the solution. Let's see how can we implement in code. So first, we are given an edge, but we want to change it to adjacency list because it's more convenient. And infinity, I'm just gonna set this to the 2 times 10 to the power of 9. As we mentioned, we're going to use the infinity to set the weight. And this weight is a 2D dictionary, which is basically used to get the real weight of an edge if the edge is a -1. So that's why in here we only set the weight as 1 when it is -1. So I do this uv and vu is because I don't know the actual order how the edge is gonna visit. So basically uv should be the same as vu because we're talking about an undirected graph here. So that's why I'm just gonna set this uv equals vu to make our life easier. Then we're gonna write our Dijkstra algorithm, and then the first one will be the mean cost of the path, and then the second one will be the actual path, that is -1. So basically the first will be the minimum cost and the second will be the path to reach that minimum cost. But I also want to filter the path such that only the -1 edge is included, because the non-1 edge, I cannot change anything about them, so I don't care for them. So this is pretty standard for Dijkstra, but just one thing is that I create a parent, which is to kind of keep track of how the next edge is called, basically how to go back from destination to source to construct the path. Usually you won't see parents in normal Dijkstra. I only use this because I want to construct the path in here later. So other than that, it's pretty standard for Dijkstra algorithm. We need a min heap, and then we keep track of the mean cost from source to everything else basically. And then confirm is an array indicating that we have reached the absolute smallest for the mean cost or not. And then we're just going to visit every node one by one in the order of the cost. So at first, we're gonna push the source with 0 cost because source doesn't cost anything to reach itself. And then we're gonna keep popping anything else. And if it is already confirmed, and we're not going to do it because the minimum has already been confirmed. Otherwise, we're gonna set the mean cost to cost, and then the confirm, we need to set that to true, and then we're gonna visit every neighbor and its weight. And if the weight is -1, we're gonna check the real weight right now instead of using -1 because we can actually set a weight on it. So we're gonna check the real cost of the neighbor, which will become my cost plus this edge weight. So if this neighbor cost is less than basically its current minimum, then I'm gonna set the parent of the neighbor to me, because from the neighbor perspective, it is the best to come from me, which is current. So I'm gonna also set the mean cost to my current cost so that it will only pick the smallest. So by the end of visiting all the neighbor, this parent should really be pointing to the parent that has the best outcome for it. And I'm gonna push the neighbor cost and the neighbor to the priority queue. After doing all of the while loop, then we're gonna reconstruct the path. And currently we're gonna set as destination, and until we reach the source, we keep visiting the parent. And as I mentioned, we don't care a path that is not inside the wait list. So by default, if it does not have the weight of -1, it will be 0. So basically this weight next now will be 0 because unset value in dictionary in Python is 0. So we're gonna check that it's not 0, and we also don't want to change anything else when it is already set to infinity. And then we're gonna add that path to here if it is actually a -1 path, and that's something that we can change. And we're gonna keep going to the next, and then until we reach the source, and then we can just get every path in the shortest path, and then just return it. So now that we have the Dijkstra, and the next helper method that we write is going to be a method called form_answer. So this basically is trying to form the answer from the weight list, and the way to do it is just reiterate everything in the edges. So if it is not a -1, it means it is else here, then we're just gonna add that normally. But if it is a -1, and we want to add the actual weight instead of -1, because we have to set the weight to something for the -1 edge. Now, having all the helper method, then we can finally start our logic. First, we're gonna just run the Dijkstra, and then if the Dijkstra returning the minimum cost now is just equal to the target, then we just directly return the answer. But if it is not equal, or until it is equal, we have to do the following logic. First, we're gonna check if it is larger than target, or there's no -1 path that we can change. Then, as we discussed, we're just gonna return. We're just going to return the empty array. And otherwise, I'm just gonna pick just random one of the -1 path. By the way, this won't be index our bound because I already checked length will not be 0 here. So there will be at least one element. So I just picked the first one. And this first UV is going to be a -1 path. And I'm just gonna check the difference of the target minus mean cost now. And also, by the way, this diff will always be positive integer, because if they are exactly the same, then I would have exit the while loop here. And if it is negative, then in here I will just return an empty array. So the diff has to be positive integer in here. So after that, we're gonna set this -1 edge to plus equals to diff, basically. So you can look at this first. Weight VU plus equals to diff. That's what it does. And I also want to set the result of this to the UV because they mean the same edge to me. And this is an undirected graph, and we need this implementation to make the weight to be equal bidirectionally. And then we're gonna change the mean cost path to a set. It is because in the following, we're going to set every edge outside of this particular edge to be infinity, as we already discussed. And we're gonna just iterate every edge. And first we're gonna check if it exists in the mean cost path before. And if it is not exist before, and this weight is a -1 that we can change, then we're just gonna make this as the infinity, because we want to make our path that we just changed to be the minimum path. So everything else to be the infinity. And then you're gonna run Dijkstra here again until we reach the target, or until we reach some boundary case that we have nothing to do about it. and otherwise when it's reached mean cost now equals target, then we will just form the answer here. So for the space complexity, it is O n plus m, where n is the number of vertices and m is the number of edges. Mainly come from this ways to the dictionary and also this adjacency list. And for time complexity is more complicated. As we know, this Dijkstra run in O n plus m log n plus m because it used the mean heap. And then, but we will keep doing the Dijkstra over and over again. In the worst case, we will run the Dijkstra m times when everything in the edge is a negative one. So m times m plus log. So this will be the total time complexity. That's pretty much all for the solution overview and the code implementation. And I will see you next time. Bye bye.